Today, we are going to discuss two important concepts with respect to hidden Markov model, the forward algorithm, the backward algorithm, the forward and backward probability values and their application in the hidden Markov model training. This algorithm is also known as the Baum Welch algorithm or forward backward algorithm. Now, the training part is important because the strings which are accepted by the hidden Markov model, and we will discuss it in the context of bigram probabilities. The states are bigram sequences. We take two sequence states, and with respect to that we find out how the parameters of the hidden Markov model can be found. We remember that a hidden Markov model is defined by its transition probability and the observation probability. The idea is to be able to learn these values. There is a very famous technique called the expectation maximization, which is at the heart of this algorithm, and we will discuss this in detail. So, continuing with the slides, forward and backward probability calculation is what we are going to do, and we make some very useful definitions. We define f k I as the probability of being in state S I having seen the observation sequence O naught, O 1, O 2 up to O k. Okay. So, this sequence is seen, this observed sequence, and having seen that the system is in the state S I. So, f k I can be written as probability of the string seen being O 0, 1 up to O k and the state after that being S I. Okay. So, it is a joint probability, the probability of two events happening with m as the length of the observation sequence. The probability of the observed sequence is the whole sequence is P O naught, O 1, O 2 up to O m, and now we employ marginalization, and this probability can be written as equal to probability O 1, O naught, O 1, O 2 up to O m, comma S p. S p is any state which comes after seeing the whole sequence of observations, and we have to make this random variable take all possible values, and so p is going from 0 to n. There are total number of n plus 1 states, and this is equal to sigma p 0 to n f m p. So, we apply straightforward the definition of forward probability, and f m p is the representation of p whole sequence of observations and the next state. So, if we sum the forward probabilities of the observation sequence and the state the machine is in after the observation sequence, then we will get the probability of the whole sequence. So, this is simply applying the law of probability, the marginalization law, and so we find that the probability of the observation sequence is equal to sigma p going from 0 to n f m p. All right. So, this is the way the forward probability is used to calculate the probability of the whole observed sequence. Now, the question that comes naturally is how do we calculate this forward probability? Okay. The final forward probability is that of the whole observed sequence. Can we do it efficiently? Can we sort of divide and conquer? Can we build the whole computation from small intermediate computations on segments of the observed sequence? So, the picture shown here clarifies a lot of issues regarding this situation. So, S 0 is the starting state, S 1 is the next state, which can be one of the states which are the constituents of the hidden Markov model. O naught is typically epsilon, where we go into one of the starting states, or if there is a unique starting state, we go there. Then O1, O2, O3, OK, OK plus 1, OM minus OM is the whole observed sequence, and after OM the system enters a final state, which can be one of the given states in the machine. So, when we do so, we find that we are transiting from state to state with the output observation OK. So, SP to SQ, there is a state transition, and OK is the observed output symbol. Now, this is a diagram which is capturing the relationship between the observed sequence and the state sequence. So, for every state there is an output symbol and a transition to the next state. So, when we have this picture in front of us, we can very easily see that the forward probability k comma q, which means nothing but observing the sequence O 0, O 1, O 2 up to OK, and then being in state S q. This is by definition, and this is equal to P O 0, O 1, O 2 up to OK minus 1. I isolate this symbol OK, the last symbol on the output sequence, and I also have this SQ. So, the whole probability expression now has 3 parts: O naught to OK minus 1, the symbol OK, and then the state SQ. Now, I introduce the state SP. So, it is helpful to look at the picture when we look at these expressions. So, what was FKQ? FKQ is referring to this part of the output sequence and this part of the state sequence. So, one sees this whole output sequence and becomes and comes into the state SQ. Now, SQ. Now, when we have SP, then surely the output symbol is the previous one, which is OK minus 1, and SP is the previous symbol. Now, since we are introducing this variable here SP, P has to again go from 0 to n, all possible states of the hidden Markov model, and therefore, a sigma sign is introduced. This is the law of marginalization, and this shows that we have introduced SP here. O naught to OK 1, OK minus 1 is the observation sequence, OK is the symbol, and SP and SQ are the states. So, one should particularly note this pattern SP, OK, SQ, where SP is the source state, SQ is the destination state, and OK is the output symbol. So, we are essentially referring to the pattern that obtains at the state and observation sequence as shown here. So, this will be our pattern of interest. Now, what we can do is that we can take this probability value and isolate the part P O 0, O 1, O 2 up to OK minus 1 and SP here. Then we have symbols up to O, then we have this symbol here SP, and this should be OK. So, P OK SQ, P OK SQ, and the conditioning part is SP O 0, O 1, O 2 up to OK minus 1. Okay. So, this is actually OK. So, now we have this part, which is nothing but F k minus 1 P. So, the probability of seeing O naught O 1 up to OK minus 1 and being in state SP. So, this is F k minus 1 P, and this particular probability here we can ignore everything other than SP, because the previous observation symbols do not influence this probability according to Markov assumption. So, P OK comma SQ given SP, and this by definition is nothing but P SP OK arrow SQ. So, this is nothing but this transition probability of going from state SP to SQ as shown here in this whole sequence, and f k minus 1 comma p is the forward probability up to k minus 1. All right. So, we have this way of computing f k comma q from f k minus 1 comma p and this transition. So, we can depict this forward probability calculation pictorially as follows. I would write this diagram. So, f k q is nothing but a summation of f k minus 1 p values, which is nothing but 0, then f k minus 1 1, f k minus 1 2, and so on, f k minus 1 comma n. And let us also throw in one more term, which is f k minus 1 n minus 1. Okay. So, we take these forward probabilities, multiply them by the corresponding transition probability values, which is nothing but f p of S 0 to S q with output symbol being O k, and this probability here would be S 1 to S q with output symbol being O k, and here this probability will be S n to S q with output probability being O k. So, this very clearly shows how the forward probability at any point in the sequence, okay, at the kth place, can be computed in terms of whatever probability value, whatever forward probability value has been accumulated so far, okay, up to k minus 1. We simply take those forward probability values for different states at k minus 1 and multiply each such forward probability with the transition probability involved, okay, and then sum them up, we get the forward probability. So, this means that the computation of these f k comma q can be done by performing an addition of n plus 1 previous computations multiplied by a probability value. So, we have n plus 1 operations giving rise to the computation of f k comma q. Okay. So, if we can write a complexity expression in the next slide. Complexity expression for computing f k comma q. Let us call this T k. T k is clearly equal to I is equal to 0 to n T k minus 1. Okay. So, this is in terms of a recursive expression, and we can write the boundary condition as f 0 comma q is equal to p q, where p q is the initial probability of being in state S q. The initial probability of being in state S q, that is S 0 to S q. So, this shows us that the forward probability can be computed very easily, and it is not difficult to show that forward probability can be computed in time proportional to the length of observation sequence. So, it is a linear time. So, it is a linear time computation. So, this expression we can take up in more detail later. In particular, what will emerge is that the forward probability or the probability of the observation sequence, which is in terms of the output in terms of the forward probabilities, this forms a lattice like structure. Okay. So, this is what we would like to show. Now, we move on to the complementary probability, which is called the backward probability. Backward probability, we call it BKI. Okay. And look at the slightly different definition of BKI. BKI is the probability of seeing OK, OK plus 1, OK plus 2 up to OM, given that the state was SI. Okay, just compare this with the definition of the forward probability. Forward probability says that we begin from the start of the observation sequence and go to the kth observation symbol, and then we note the state we are in from there. In backward probability, we start from the kth observation symbol, go on up to the end of the string, and this is the observed sequence given that the state was SI. Okay. So, BKI can be written now as probability of seeing OK, OK plus 1, OK plus 2 up to OM, that is the end of the sequence, given that the state before outputting OK was SI, with M as the length of the observed sequence. So, P observed sequence therefore, can surely written as P O0, O1, O2 up to OM, which is equal to P O0, O1, O2 up to OM, given that the state was S0, which is always true, and that can be written simply as B 0 0. Okay. So, we take the probability of observing O0 to OM, given that the starting state was S0, which simply is B 0 0. So, now you can compare that P probability of the complete observed sequence could be expressed as a sum of forward probabilities, and the probability of the same observed sequence is nothing but a single backward probability with arguments 0 0. Now, we try to see again, just like forward probability, how the backward probability can be calculated. And again, this state sequence is which was also used for forward probability calculation. So, we have the observation sequence O0, O1, O2, O3 up to OM, which is the last observation symbol, and S0, S1, S2, S3 etc. are the state symbols with S final as the final state. Now, each of these S1, S2, S3 etc. can be one of the constituent states of the hidden Markov model. All right. So, we take up this expression P OK, OK plus 1 up to OM given SP. Okay. Now, this again can be broken up into two parts. We isolate the part OK and leave this part OK plus 1 to OM, and the conditioning part remains same, which is SP. And now we introduce a margin variable, which is SQ, and SQ you can see here is the state at this point in the state sequence after OK. So, this is the picture, and we correspond this with the picture here. Now, this is sigma q 0 to n p OK comma SQ comma SP. So, this part I isolate, this particular pattern I isolate OK comma SQ given SP. So, we are doing nothing but trying to capture the probability of this pattern, which obtains as at the output and observation sequence. Okay. So, P OK comma SQ given SP, and then we have the other probability part P OK plus 1 OK plus 2 up to O m, and now I apply chain rule. So, OK and SQ come as the conditioning part, and SP is of course there. So, this particular part P OK comma SQ given SP is written here, and our part here P OK plus 1 OK plus 2 up to O m given OK SQ SP can simply be written as P OK plus 1 OK plus 2 up to O m given SQ. Okay. So, this becomes the probability expression, because this observation sequence is not influenced by anything other than the state from which it started, which is SQ. So, look at the picture here OK plus 1 OK plus 2 up to O m, the state before OK plus 1 was SQ, and this is the only thing which influences this whole observation sequence. This is by virtue of the Markov assumption. All right. So, this is what we have here, and P OK comma SQ given SP is nothing but the probability of this transition SP to SQ with the output symbol OK. So, therefore, we can write BKP as equal to BK plus 1 Q PSP to SQ with output symbol OK, and Q going from 0 to n on the sum here. So, from this again we can write a small expression for the calculation of the backward probability BKP. So, when we write on the paper, BKP can be seen to be simply implemented by B k plus 1 0, B k plus 1 1, B k plus 1 1, then B k plus 1 2, and then B k plus 1 n. Okay. So, this is what is the expression which is used for computing BKP, and we have to sum these probability values after multiplying each of these backward probabilities with the probability of SP BKP. So, probability of SP to S0 on OK, probability of SP to S1 on OK, probability of SP to S2 on OK, probability of SP to Sn on OK. So, we have these probability values which are computed from a shorter string, because k plus 1 to n is a shorter string compared to k to n, the total length of the string starting from k, and we multiply these by the probability values here. So, again the time complexity will be exactly like the forward probability, and we have a linear time algorithm for computing backward probability. Thus, we have found two very important probability values, the forward probability and the backward probability. So, both these probability values can be computed by making use of a recursive expression, and the expression is such that for both very efficient linear time algorithm exists. Okay. So, for the whole output sequence we can get the forward probability in time proportional to length of the output string. Similarly, we can express this probability value in terms of backward probabilities, and again this is a linear time algorithm. Okay. So, let us summarize what we have learned. You can look at the slide here, and for any observation sequence and the corresponding state sequence, we have a notion of the kth place, okay, and we can compute the forward probability up to any point in the observation sequence, and we can compute the backward probability from any point to the end of the output sequence, okay, for any point in the string. Okay. So, let me just repeat this point. For any point in the output sequence and the corresponding state sequence, we can compute the forward probability up to that point and the backward probability from that point up to the end of the string. One point needs completion, which is that the backward probability needs a boundary condition. So, B k p we have seen is equal to sigma q equal to 0 to n b k plus 1 q into p s p to s q with OK, and this k plus 1 goes on increasing towards end of observation sequence. All right. So, we must have a boundary condition. So, we write this boundary condition here. Boundary condition for B k p. So, if you look at the slide, the boundary condition is very clear. The boundary condition is that having observed the last symbol in the whole sequence, the system can be said to be in a final state. All right. So, this should give us the boundary condition. So, we can say that from S m to the final state S final on outputting O m, okay, is the boundary condition. Okay. Otherwise, we can also propose an epsilon transition here, and from there we can say that there is a final state with respect to one of the states of the hidden Markov model. So, the probability of going to the final state from the last state S m is the boundary condition. So, this would be for B k p is obtained from the last symbol. So, we essentially have to write B m final, where S final is one of the states of the H m n. All right. So, this gives us a complete picture about the forward and backward probabilities, which are useful for various calculations in hidden Markov model. All right. We now proceed to how the training of the hidden Markov model is done. The problem of part of speech tagging. We have chosen a particular problem here, the problem of part of speech tagging. We have a sequence of words here, people laugh aloud, people laugh aloud, and there is a symbol hat which starts the sentence and a dollar symbol which ends the sentence. So, for hat the tag is hat itself, people is noun, so underscore noun, laugh is a verb, so underscore verb, aloud is an adverb, so underscore adverb. So, these part of speech symbols are non-standard, non-conventional. We simply use this for the purpose of illustration. So, our problem is to train a hidden Markov model from this kind of training data, where this is a supervised situation, but it is also possible to have situations where the output sequences of the machine are given, and from there we have to estimate the parameters of the hidden Markov model. So, this is a bit of a digression, where we say that one example where hidden Markov model is used is in part of speech tagging. There is a corpus. Corpus can be either spoken or written. Under spoken corpus, we have many famous ones. A very well known corpus is the switchboard corpus, which records many hours of telephonic conversation. And under written corpora, we have famous things like Brown corpus, which has about 1,000,000 words, British National Corpus, which is about 10,000,000 words with tags, and so on. So, here is a listing of famous text corpora of English: American National Corpus, Bank of English Corpus, British National Corpus, Corpus Juris Secundum, Corpus of Contemporary American English, Brown Corpus, International Corpus of English, Oxford English Corpus, Scottish Corpus of Text and Speech. So, these are well known corpora. Now, what about the tag set? The tag set is a very important concern in any part of speech tagging. We have remarked in one of the previous lectures that there is no point giving detailed and intricate tags if they cannot after all be assigned from a limited context around the word, which is the part of speech tagger's task. So, here we have some tags from a very famous corpora called Penn Tree Bank tag set. CC is the coordinating conjunction, CD is a cardinal number, DT is a determiner, X is an existential there, FW is foreign word, in is preposition, JJ is adjective, JJR is comparative adjective, JJS is superlative adjective, LS is list item marker, MD is modal, NN is noun, NNS is plural noun, NNP is proper noun. So, a few of these tags in the Penn Tree Bank are shown here. Now, all these tags have different examples. For example, CC is the coordinating conjunction, and it can be used for entities like but, and, while, and so on. Now, how is this tag set created? The tag set is created by lot of lot of insight into the way the language operates and the words in the language are placed with respect to each other. All right. So, some points of thought are: why is it that English has a tag for singular noun and a separate tag for plural noun? Now, one of the important reasons for this is that in English most nouns can be used as verbs. So, the plural form of a noun is almost always same as the singular number third person present tense form of a verb. So, like John plays, plays is the third person singular number present tense form of play, and we saw many plays. Here plays is a noun, and both these categories, that is third person singular number present tense form of verb and plural noun, both of them are very frequent in the language, and the system cannot afford to make mistake with respect to their tags, and hence it has become necessary to separate the noun singular tag and the plural noun tag. So, similarly, each tag has a lot of linguistic considerations and computational considerations behind it, which we can discuss at some point of time. So, hidden mark, we come back to hidden Markov model training, and this is very famously known by Baum Welch or forward backward algorithm. So, the key intuition here is that we have a hidden Markov model. We start with some probability values assigned on the arcs, capturing the probability of transition from state to state with a particular output symbol, and then we use an expectation maximization like algorithm for training the HMM. So, if we take the ARN example again, then in the ARN example we have all the numbers of red balls and so on, but what is not given to us is this transition probability table and the observation probability table, and we have seen before that these two probabilities can be merged to have a probability value marked on the arcs. Now, suppose this observation is given, which is corresponding to the hidden Markov model R, G, G, B, R, G, R. Then the Viterbi question was what is the corresponding state sequence. What we ask is that if the state sequence is given, if the state sequence is given, that would be a supervised situation. If only the observation sequences are given and the structure of the hidden Markov model is given, then how can we estimate the transition and observation probabilities. So, this is a question. In this Markov model, we have hidden Markov model, we have given the observation and transition probabilities, and they have been combined to produce this kind of probabilities on the arcs, and we have this kind of observation sequences. From the observation sequences, it is possible to go through either one single state sequence or a number of state sequences. Okay, but what is given is the observation sequence, and we can go through multiple state sequences for one particular observation sequence. When that happens, how do we get the parameters of the FSM? So, Viterbi discuss this question of give the best possible state sequence given the observation sequence. We have seen how hidden Markov model and the Markov assumption can do this job. Now, we come to the Baum Welch algorithm, and this is in terms of counts of the transitions in the output observation sequence. So, to understand this point, let us take a sequence here A B B A A A B B B A A A. So, A B B A A A B B B A A A, these can be produced from a state sequence of this kind. Okay. And if this is the only state sequence which produced the observation sequence, then we can compute, we can make a good estimate of the probabilities of transitions and the output symbols just simply by counting the transitions and the outputs. So, in this particular observation sequence and the state sequence, corresponding state sequence, we find that Q to R transition with output symbol A occurs 5 times. Q to Q transition with output symbol B happens 3 times. R to Q transition with output symbol A happens 3 times. R to Q with B happens 2 times. So, from this observation, we can propose that the probability of Q going to R on A is 5 by 8 and probability of Q going to R on B is 3 by 8. So, the Q to R transition is the only transition from state to state possible when the starting state is Q, and there are 2 possibilities of output being A or B. So, we have therefore, the probability of P Q going to R on A is 5 by 8. There are 8 cases of transition from Q, and then if we capture the next state as R and different symbols as A and B, then this is what the probability comes out to be. So, this can also be expressed by a formula here. Probability of S I to S j with output symbol W k is nothing but the number of times S I goes to S j with W k, and this is divided by all the cases of S I going to different states S L with different output symbols W m. That is why there are 2 sigma symbols here. One is for all possible output symbols and the other is for all possible destination states. So, this is a simple formula which will work in terms of exact frequency values if an observation sequence produces a single state. But problem is that we have non-deterministic transitions and then multiple state sequences are possible for a given output sequence. So, our aim is to find the expected count through this. So, the whole computation happens by an interplay between a probability calculation in terms of counts and estimating the counts, expected counts rather, from the values of the transitions, the number of times the transition occurs, and weighting it by the probability of state sequence given the observation sequence. Okay. So, this is illustrated by an HMM here. This is the actual desired HMM and this is the initial guess of the HMM, and from this we can find out the path probabilities and from this we can make another estimate. So, this particular algorithm we will discuss in detail in the next lecture, and we will see that this produces a very interesting algorithm for training the HMM.